Welcome back to the Java's OCP 21 series. I'm Arup from ClusterMicro Technology. The OCP 21 syllabus objective states using generics including wildcards, use a Java array and list, set, mapped and Deque collections. There are other things we will discuss later. So this module covers the full range from the most basic fixed size array through to the specialized double-ended queue. Each collection type has a specific purpose, specific characteristics and specific exam traps. Everything in the Collections API is built on top of concepts you first encounter with arrays. Indexing, sizing, sorting, searching. And the exam tests arrays not just on syntax but on the precise behavior of the utility methods in the java.util.arrays class. So you call arrays.binary search on the array and the value is not found. What does it return? Most people say -1. So that is wrong. It returns a negative value but not necessarily -1. It returns a specific negative value that encodes where the element would have been inserted. So we have arrays.sort nums. Okay. Arrays capital A here is a utility class in java.util. It provides static methods for common array operations. You never create an arrays object here. Okay. You call the methods directly on the class. Then we have arrays.sort nums sorts the array in place, okay, modifying the original array. The elements are rearranged into ascending order. For primitive arrays like int, the sort uses a dual pivot quick sort algorithm internally, okay, which runs in O n log n time. In place means nums itself is modified. There is no return value here. After this call, nums is sorted, okay. For arrays of objects like string, arrays.sort uses a team sort and sorts in natural ordering. Okay. For string, natural ordering is lexicographic, alphabetical. So Ali is before Bob and it is Bob is before Charlie. For custom objects, class must implement comparable or you must provide a comparator as a second argument. Arrays.sort names, comparator.reverse order. So it will reverse in alphabetical way. So critical point for binary search is the array must be sorted before calling binary search. If you call binary search on an unsorted array, the result is very undefined. Okay, the method may return a wrong index or wrong not found value. The OCP exam will test this. Then we come to arrays.binary search. int idx equal to arrays.binary search nums, 3. So arrays.binary search nums, 3 searches the sorted array nums for the value 3 using binary search. Okay, binary search works by repeatedly halving the search range. So it is O log n much faster than linear search for larger arrays. Okay. So if the value is found, returns the index of the found element. If there are duplicates, there is no guarantee which index is returned. It could be any occurrence. And if the value is not found, then returns a negative value. So, but not simply -1. The formula is minus insertion point -1, where the insertion point is the index at which the value would be inserted to keep the array sorted. For example, if you have nums is equal to 1, 2, 4, 5, 7, search for 3, but 3 is not in the array. 3 would be inserted here at index 2 between 2 and 4 and return value would be -2 -1 equal to -3. So another example is search for 0 in the same way. 0 would be inserted at index 0 before everything. Return value would be -0 -1 is equal to -1. Search for 10. 10 would be inserted at index 5. Everything after everything. Okay. So return value would be what? -5 -1 equal to -6. Okay. The formula always gives a negative number. The only way to get a -1 back from binary search is if missing element would be inserted at index 0. So saying binary search returns -1 for not found is only sometimes correct and the exam exploits this. Okay. Then we come to arrays.copyof. int copy equal to arrays.copyof nums, 10. Creates a new array of the specified length and copies elements from the original into it. So the new array is a completely separate object. Modifying copy does not affect nums and vice versa. Okay. two scenarios depending on the new length here. So new length smaller than the original. Only the first elements up to the new length are copied. The rest are truncated. New length larger than original. So the original 5 elements are copied. The remaining 5 positions, indices 5 through 9, are filled with the default value for the type. Okay. For int, that is 0. So if nums was 1, 2, 3, 4, 5 after sorting, copy would be 1, 2, 3, 4, 5, 0, 0, 0, 0, 0. The original 5 values followed by 5 zeros. There is also arrays.copy of range original from 2. Copy is a specified range. From is inclusive, 2 is exclusive. The same convention as substring. Okay. Then we have arrays.fill, arrays.fill nums, -1. So arrays.fill nums, -1, it fills every element of the array with the specified value. After this call, all 5 elements of nums are -1, that is -1, -1, -1, -1, -1. So this is a destructive operation. The previous contents of nums are overwritten. Okay. So there is no way to recover the previous values after fill. Okay. So there is also a range version, arrays.fill nums 2, 4, -1 fills only indices 2 and 3 with -1. Again, the end index is exclusive. Then we have arrays.toString. So arrays.toStrings nums say, okay. So system.out.println arrays.toString nums converts the array to a human readable string in the format bracket element 0, element 1, element 2, etc. So for nums -1, -1, etc., this produces within bracket -1, -1, etc. Okay. So this is the correct way to print an array. Without it, system.out.println nums will print something like within bracket I @7852e922, etc. That is the array's memory address. Completely useless for reading content. Always use arrays to string to print array contents. Okay. For two-dimensional arrays, use arrays.deep-to-string matrix. This handles the nested structure and produces 0, 0, 0, 0, then 0, 0, 0, 0, and 0, 0, 0 for our matrix. Okay. So, and how do you compare arrays? We have nums equals copy. It will be always false for different array objects even if contents are identical. Equals compares references. Arrays.equals nums, copy compares elements by element, okay, and returns true if same length and all elements are equal. Then we have arrays.deep equals matrix 1, matrix 2. For two-dimensional arrays, compares element by element recursively. So never use nums.equals copy because arrays inherit equals from object, which compares references just like equals. It never compares contents. This is a common mistake and OCP exam trap. Now we are going to discuss list, set, map and deque. The 4 interfaces we are covering here is list, set, map and deque. Each solve a different problem. The exam tests not just the syntax of each but the specific guarantees each one makes and critically which implementations you should use and when. So let me give you the one sentence summary of each before we read the code. Okay, so we have list, which is ordered, allows duplicates, index-based access. Set has no duplicates, typically unordered. Map is key value pairs, each key is unique, values can duplicate, and deque is double-ended queue. Works as both a stack and a queue. Okay, each one has multiple implementations with different performance characteristics. The exam will test the differences. So let us go through each. Okay. So we have list, string list, new array list, list.add a, list.add b, and list.add a, then collections.sort list. Okay. So we declare the variable as type list string, the interface, and create an array list string, the implementation. This is the correct pattern. Okay. Always program to the interface on the left side. If you later decide to switch to linked list, you only change the one line. Okay. So list is the interface in java.util. It guarantees elements are stored in a specific order, insertion order by default. Then duplicate elements are not allowed and elements can be accessed by index. Okay. ArrayList is backed by a dynamic array internally. It is the most commonly used list implementation. Random access by index is O1, okay, extremely fast. The diamond operator on the right is called diamond operator. Java infers the generic type from the left side, okay. You do not need to repeat string on both sides. So key list methods the exam will test is add element, add, and that adds to end. And then add index comma element, inserts at index, shifts to right. Then get index, retrieves by index, and then remove index, removes by position, remove object, removes first occurrence by value, set index comma element, replaces at index, and size, that is number of elements, then contains element, true if element present, and index of element, index of first occurrence, -1 if not found, okay. Then we come Collections.sort list. Collection with capital C is a utility class in java.util that provides static methods for collection operations, okay, similar to arrays for arrays. And Collection.sort list sorts the list in place in natural ordering, okay. For string, natural ordering is lexicographic. After sorting, list will become A, B. Collections also provides Collections.reverse list, then Collections.shuffle list, Collections.min collection, Collections.max collection, and Collections.frequency collections, element. The exam will test them. And ArrayList versus LinkedList, if you see, ArrayList will be fast random access, slow insert and delete in the middle, and best for read heavy, index heavy access, okay. But LinkedList is slow random access, fast insert delete at known position, also implements Deque, best for frequent insertions and deletions at either end, okay. Now we come to set. So here we have set integer set equal to new HashSet list of 1 2 3 2 1, okay, and set integer sorted equal to new tree set set. Set is the interface that guarantees no duplicates. Here we create a HashSet using a list that contains duplicate, list.of 1 2 3, 2, 1. So when HashSet receives these values, it silently ignores duplicates. So there will be no error and no warning. It simply keeps the unique values only. So the final set will contain 1, 2, 3. So a very important exam point is HashSet does not guarantee ordering, okay. So the iteration order may look very random, differ from between JVM runs, and must never be relied upon. Internally, HashSet uses hash code and equals to determine uniqueness. Two objects are treated as duplicates if equals true, okay. So that is why proper implementation of equals and hash code is critical for custom objects. Another common exam trap is set.add element. It will return a boolean, okay. So we have here set integer equal to new HashSet, then system.out.println s.1, it will be true, and if we do system.out.println s.1 is.add1, it will be false, okay. True because element is added successfully, and false because duplicate is rejected. So now look at set integer sorted equal to new tree set set, okay. Tree set is another set implementation, but unlike HashSet, it maintains sorted order, okay. So when we pass HashSet into the tree set constructor, all elements are copied, then automatically they are sorted. Result will be 1 2 3, so in ascending order. Tree set internally uses a red black tree, so add, remove, contains are all O log n, okay, which is slower than HashSet, but you gain sorted ordering, okay. So important set implementation is that HashSet no ordering, fastest average performance, uses hash code and equals. And linked HashSet, it maintains insertion order, slightly slower than HashSet. And tree set maintains sorted order, implements navigable set, and supports first, last, head set, trail set, okay. Now we are going to discuss map. So we have here map string integer map equal to new hash map, map.put a, 1, then map.put b, 2, map.get or default c, 0, map.put if absent a, 99, and map.forEach k, v, system.out.println k plus v. Okay, map stores data as key value pairs. So important rule is keys must be very unique and values must be very duplicate. So hash map is the most common implementation here. It provides average O1 performance for put and get, but no ordering guarantee. Okay, very important exam point is map does not extend collection. It belongs to a separate hierarchy. Then we have put map.put a comma 1. It stores a key value pair. If the key already exists, the old value is replaced and put returns the previous value. Okay. For example, integer old equal to map.put a comma 99. It will return 1 because 1 is the old value. Then get or default. So we have here map.get or default c comma 0. If the key exists, then returns its value. Otherwise, returns the default value. So map.get or default c comma 0, it will return 0 because c is missing. So before Java 8, this required manual null checks. Okay. Then put if absent, map.put if absent a comma 99. This only inserts the value if the key is not already present. Since a already maps to 1, this call does nothing. Okay, so map.get a still returns 1. This is called a no op. Then we have for each. Map.forEach k comma v system.out.println k equal to plus v. Okay, so for each accepts a by consumer. The lambda receives a key and a value for each entry. For hash map, iteration order is very unpredictable. So output could be a equal to 1, b equal to 2, or b equal to 2, a equal to 1. Never assume ordering with hash map. So important map methods are get key, contains value, remove key set, values, entry set, size, etc. Okay. So important map implementations is hash map. There is no ordering, allows one null key, allows multiple null values. Linked hash map preserves insertion order, and tree map sorted by keys, right? O log n, and implements navigable map. Now we are going to discuss Deque. Deque string Deque equal to new array Deque, Deque.push x, Deque.push y, Deque.pop, Deque.offer z, and Deque.poll. So Deque stands for double-ended queue. It is pronounced as Deque. So it allows insertion and removal from both ends. A Deque can behave as a stack LIFO or a queue FIFO. Okay, first in, first out, and last in, first out. Okay, so array Deque is the preferred implementation for both. The old stack class is considered very legacy. So let's discuss the stack behavior here. LIFO, Deque.push x, and Deque becomes x. Now we are going to call Deque as Deque from now onwards. Okay. So Deque becomes x. Then we have Deque.push y. Deque becomes y comma x. Now Deque.pop returns y because stack behavior is last in, first out. So after pop, it will be x. Okay. So if the stack is empty, pop will throw no such element exception if it is empty. Okay. Now let us discuss the queue behavior for FIFO. So current Deque is x. Then if we do Deque.offer z, Deque becomes x comma z. Okay, now Deque.poll will return x because queue behavior is first in, first out. Okay, so Deque after poll is z. Okay, an important difference is poll returns null. Okay, if it is empty, it does not throw exception. Okay. So if we do stack usage summary here, we will see push, pop, and pick behavior is LIFO, last in, first out. And if we see queue usage summary here, so it is offer, poll, and pick behavior is FIFO, first in and first out. Okay. So pick and poll are very important in Deque and queue operations. Okay. So if you see pick, so it will mean look at the front element without removing it. So now we are going to discuss offer. So offer means an element, add an element to the queue or Deque. Okay, usually added at the back or tail. So if we have a Deque string Deque, new array Deque, Deque.offer a, Deque.offer b, system.out.println Deque will get output as ab. And queue behavior offer follows FIFO, first in and first out. So a is added first and b is added later, front and back. And And peek is look at the front element. It means look at the front element without removing it. Okay, so we have deque string deque equal to new array deque. So deque.offer.a, deque.offer.b, system.out.println, deque.peek. So output will be A. Okay, because deque still contains A, but because peek does not remove anything. Okay, and if we do poll, it means remove and return the front element. So here if the deque has A comma B, and if we do system.out.println deque.poll, we'll get output as A, and deque now becomes only B because poll removes the first element. Okay, that is the difference. That is peek, it will not remove, it will remove, but poll it will remove. Okay, and in both cases peek and poll, if the deque is empty, it will return null. Okay, discuss poll and deques. That is a very important topic for OCP. So what is poll? Poll is used to remove and return the head. That is the first element of the deque. Key points are array deque. Most common implementation of deque is poll O1. It is very fast. Okay, it removes the front of the queue. If the deque is empty, poll will return null. That is the safe version. Okay, so deque is very flexible. When we use it as a stack, we mainly use these three methods. Okay, push element. So what it does is that adds an element at the front top of the deque, and speed is O1. It is very fast. Think of it like putting a new plate on top of a stack of plates. Okay, then pop, what it does is that removes and returns the element from the front of the deque. Speed is O1. And if deque is empty, it throws no such element exception. So you can think of it as like take the top plate of the stack. Okay, and peek is what it does, returns the element at the front top without removing it. Okay, speed is again O1, that is fast. If the deque is empty, it returns null. Okay, so think of it, just look at the top plate without taking it. So now we are going to discuss big O complexity for collections. It is when you see O1, O log n, On, etc., it means how performance grows as data size grows. Okay, the exam loves this. Okay, imagine n is equal to number of elements. So 0 to O1 is constant time. Okay, performance stays almost the same regardless of size. Whether 10 items or 10 million items, operation speed is nearly constant. Example, HashSet.contains x, HashMap.getKey, ArrayList.getIndex. These are example of O1. Okay, that is constant time. Why ArrayList.getIndex is O1? Because list.get 500, Java directly jumps to memory location. Like shelf number 500, directly go there. Okay, so no searching is needed. Then we are going to discuss O log n, logarithmic time. Okay, so meaning very fast scaling. Each step cuts the search space roughly in half. Okay, say example is tree set, tree map, binary search, etc. Why tree set is O log n? Because it internally uses red black tree. So each comparison, it narrows possibilities like dictionary lookup, middle, left, right, half, then repeat. Okay, it is very efficient. Then we come to ON, that is linear time, meaning needs to scan elements one by one. If data doubles, work roughly doubles. Okay, for example, ArrayList.contains, LinkedList.getIndex, then HashMap.contains value. Why contains value is ON? Because map.contains value say ABC. The map has fast access by key but not by value. So Java checks every value one by one. Okay, so that is why it is ON. So most important things here is that ArrayList is good at random access, bad at middle insert and remove. Okay, and LinkedList is good at front, back, insert, remove, but it is bad at random access. And HashSet and HashMap is it is very good at raw performance O1 but no ordering. Okay, tree set, tree map is slower O log n but sorted ordering. Okay. So one example is that students sometimes memorize hash map is equal to O1, but the exam may ask contains value, right? So that is ON because values are not hashed separately. Okay. So let us discuss the Java collection complexity cheat sheet. Okay, so if you see array list, we have get index, that is O1. It is super fast and direct access like any array, direct access like an array. Then we have set index comma value, that is also O1, also direct access. Then add at the end O1 on average and just append. Okay, then add and remove in the middle, but that will be ON, have to shift because they have to shift all elements after it. Okay, then if we go to linked list, then add first and add last will be O1 because it is very fast, because we have head and tail pointers. Then remove first also is O1. Okay, but if you do get index and contains, that will be O1 because they have to walk through the list from the beginning, and for contains they have to traverse. Okay, then HashSet will be add remove contains, it is O1 average, no problem. And it because it uses hash code and equals to work is magic. Okay, tree set, if you see add remove and contains, it will be O log n. It is slower because it keeps everything sorted in a tree. And hash map is put key value, get key, contains key, it is O1 average. Okay, and contains value ON because this is the trap, values are not hashed here. Okay, tree map, we have put get and remove O log n, they keep keys sorted. Okay, and array deque, it is based for stacks and queues, offer, poll, peek, push, pop, all will be O1. Okay, extremely efficient at both ends. So most important patterns to remember is that array list, it is good at random access, getting by index, but it is bad at inserting or removing in the middle. Linked list is good at adding and removing at the front and back, but it is bad at random access. HashSet or hash map is best speed O1 but no ordering at all. Tree set or tree maps, it is slower O log n, but they give you sorted ordering. Okay, so exam goal rules is ordering usually cost performance. Okay, if you want fast ordered, usually pick linked hash map, insertion order, or tree map, sorted keys. Okay, but the trap is everyone remembers hash map is O1 but contains value is actually ON because values are not hashed. So final quick summary is array list is best for fast indexing, linked list best for fast insert and remove at ends, HashSet fastest uniqueness, tree set shorted uniqueness, hash map fastest key lookup, tree map shorted keys, and array deque or deque best for stack and queue. Okay.